Okay, so let's keep going on with our stoichiometry of solutions and start to look at dilution. Okay, so the important thing here is that the calculations that we're going to be looking at are referring to when we are mixing solutions, but no reaction, okay, no reaction is occurring. Okay, which means that we really need to think about the definition of dilution being that we are adding more solvent to a solution. Okay, so what we're talking about here is that N being the amount of substance doesn't change. Okay, so all we're doing is changing the volume that N is dissolved into. Okay, so if I have a glass of cordial and it has a certain percentage of sugar syrup in it or flavoring, then what we're actually talking about in this case is that we are going to add, some extra water. Okay, and increase the overall volume. So now that what was dissolved in here has now spread throughout the solution. We haven't added any more solute, we haven't added any more stuff that's been dissolved into it, we've just increased the amount of water. So if we think about it, if we have a solution, we're looking at the particles inside it. When I dilute, I'm really just increasing the space between the solute particles. Okay, so we're just adding water. There's no reaction occurring, so we can't use this for if we mix an acid with a base or do a precipitation reaction or anything like that. What we need to use it for is when we are adding water to a solution, or the term is often used as making up a solution. Okay, so we often do this because we are given what we refer to as a stock solution, and if you think of this as like stock concentrate with cooking, okay, where you've got chicken stock or beef stock that is there to add flavor, but it's usually more concentrated. We've concentrated down those flavors. So with a stock solution for chemistry, we have a higher concentration. Okay, and we usually make this because we don't want to keep large volumes on hand, because that makes storage problems and sometimes safety problems. So we have this stronger stock solution that when we want to do particular reactions, if we want a particular concentration, we will dilute that stock solution up to get the concentration that we need. Okay, so when we do that, we're not changing what it is or what it's made of, we're just diluting it up to get the right concentration. So just a reminder, the number of moles isn't changing when we dilute the solution, but the concentration does because we change the volume. So we can use this equation, and this equation is a proportionality, and it stays this way because what we can do is we know N is constant. So remembering that N is equal to CV, if N is constant, then the CV, when multiplied together, must equal the same thing because N isn't changing. So we get this proportionality equation. So the key thing that we need to remember from this is C1V1 is just your initial concentration, what you're going from. Okay, and C2V2 are values from what you're going to. Okay, so your initial and your final. Okay, so we need to find the initial concentration, which will of course appear in our question in moles per decimeter cubed, the initial volume of our solution, which will appear in centimeters cubed or decimeters cubed, and in this one there's no need to convert. Okay, all you've got to make sure is that volume units must be the same for both sides. So if you plug in a centimeters cubed value into V1 and you're solving for V2, then your volume will be in centimeters cubed. Okay, if you're subbing in a decimeters cubed value into V1 and solving for V2, then your answer will be in decimeters cubed. Okay, so you need to be aware of that. And then your concentration, if you're solving for concentration and the one that you put on one side is moles per decimeter cubed, then that will be what your concentration ends up on the other side. Okay, so as long as they both match, there's no need to convert. So let's have a look at an example question so we can see how this actually works. Okay, so we'll notice here we need to look at the terminology, and we have 600 centimeters cubed of deionized water is being added to 50 centimeters cubed of 0.3 mole per decimeter cubed HCl solution. So what we're saying is that we had a 0.35 mole per decimeter cubed solution of HCl, and then we came along and added 600 centimeters cubed of H2O. So it's just H2O, so I'm looking at dilution, and you will notice that diluted is also present in my question. So that should tell me straight away I'm going to use C1V1 equals C2V2. It wants me to determine the concentration of the diluted, so this is the final solution. Okay, sorry for that flicking backwards and forwards. Okay, so the final solution, so we're looking for V2, so I'm going to rearrange my equation, and I'm going to get V2 on its own by taking C1V1 and dividing by C2. Okay, and I need to identify what each of my values are. Whoops, sorry, we're not searching for V2, we're searching for C2. Okay, let's try that again. C2, C1V1 over V2, there we go. Okay, so now we've got it rearranged for the right quantity. We need to identify each of these variables in our equation. So, key things here. We have 50 centimeters cubed, which is a volume, and that is related to our initial solution. So that is going to be my V1. I have 0.35 moles per decimeter cubed, and that is related to this volume. So that is going to be my C1. Here's the catch. They haven't given us a final solution. What they've said is that they have added 600 centimeters cubed, which means that my final volume is going to be my initial 50 plus another 600. So V2 is actually going to equal 650 centimeters cubed. Okay, and you always need to make sure that you're looking for the terms added to or made up to, because added to means I bring them together. Made up to means that our final volume is that value. Okay, so in this case we've had it added to, so V2 is 650, so we're going to get C2 is equal to C1, which was 0.35, multiplied by V1, which is 50, divided by 650 is going to be, and we would expect the concentration to go down because it has been diluted, which means that we would have less substance per volume. And when we add this together, and well, not add it, but do the calculation, we get 0.269 moles per decimeter cubed. Okay, so this one was where we were diluting. We've added the two volumes together and we're working for the second concentration. In this case, in our second example, we have a 0.7 mole decimeter cube solution. Okay, so this is a concentration of sulfuric acid, which I should be thinking H2SO4 if you haven't learnt that formula yet, was formed. So this tells me that this is where I finished up. So that's got to be C2. From diluting, so this is telling me I can use C1V1 equals C2V2. And a 2 molar stock solution. So that is confirming that I had it right. This is actually my initial concentration here. So C1 is 2.00 moles per decimeter cubed. C2 is 0.70 moles per decimeter cubed. Okay, and then V1, we do know the stock solution Oh no, this is V2. So diluting 2 molar stock solution to 50 centimeters cubed. So this is like saying made up to 50 centimeters cubed. Okay, so we want to find the volume of the stock solution. So we want to find V1. So V1 is going to equal C2V2 over C1. And that is going to be, so C2V2, so we've got our 0.70, and V2 is 50 centimeters cubed. Note that I am not converting it, I'm just using it as centimeters cubed, and then I'm going to divide by C1, which is 2.00, and I will get 17.5 centimeters cubed of stock solution was used. Okay, so I can measure out 17.5 centimeters of this stock solution, make it up to 50 centimeters cubed, and I know that I would end up with a 0.7 moles per decimeter cubed solution. Okay, that's it for dilution, and we will go through some of those other example stoichiometry questions in another video.